Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to tackle with the problem of finding the arc length of the curve on the given interval, but the curves are parametrized. So this was a problem that we tackled earlier as an application of integration in the previous sections of calculus. But this time we're given the curves in the parametric form, so we should be able to use the formula derived for finding the arc length of parametric curves. Please refer back to this table. In fact, that tells us that if you have x and y coordinates of the curve parametrized by f and g, then the arc length formula that we had earlier is changed into something like this. That there you have x prime and y prime. These are the derivatives with respect to the parameter t. Squared all the way, and then we take the sum, take the radical, and integrate it from t equals a to t equals b. So this is sort of like the version of the arc length formula written in, for a parametrized curve. So as I said, this is a very classical problem of calculus, and I'm going to split the video into two parts, and we're going to tackle with each case in this video. Let me just see if I can give you more heads up for the curves here. So I have the first curve, first parametrized curve, having this kind of graph. So that means, like, think about this as like a string attached to a wall at the origin, and then the string is curved. So you're trying to find the length of the string. And in the second case, let's see what kind of graph we have. That's another parabola, in fact. And you can see that the string's attached at the left corner over there, and then going all the way up. And we're going to try to define or find the length of this string. All right, so let's get started. All right, let's handle the first part. We have x equals 6t squared, y equals 2t cubed, and t's are ranging from 1 to 4. Let's go back to the formulation just to refresh our minds that arc length formula is requiring to find dx over dt and dy over dt, and that's what we're going to do. And a and b are the lower limit and upper limit of the t values. In this case, it's going to be 1 and 4. Okay, so why don't we go ahead and look at dx over dt and dy over dt. Okay, so dx over dt is 12t, and dy over dt equals 6t squared. I'm going to go ahead and write down the formula for the arc length. So dx over dt squared, dy over dt squared dt, and here the lower limit is going to be 1 and upper limit is going to be 4. Okay, good. So what I'm going to do next is to plug in dx over dt and dy over dt. Okay. It's radical 144 t squared, 36 t to the 4th. Okay, dt. And one thing I can do here is that I can factor out 36t squared inside the radical. Okay. And I get 4 plus t squared. Okay. All right, so 36t squared is the perfect square of 60. I can pull that out of the radical. And now I'm down to 4 plus t squared, radical 4 plus t squared dt here. Okay. All right, this is like at this moment, in fact, you can pause the video and check what the best strategy is to handle this integration. But I think u substitution is the best here, because if you call inside the radical u, you have a t-related term outside the radical, so it could be easier to handle that. So to sort of like handle the u substitution, I'm going to have this scratch space here. So all I need is 60 4 plus t squared indefinite integral version of that for the u substitution to be like 4 plus t squared. Okay, so that du is in fact 2t dt. Okay, so now this integral is now, since 2t dt is du, I have 6t dt, so it's going to be 3 times radical u du. And write it as like u to the power of 1/2 and integrate 3 times u to the 3/2 divided by 2/3. Okay. I'm sorry, 3/2. And if you flip the bottom over, you have 2/3, obviously. So then this becomes 2 times u to the 3/2, essentially, plus c. But I don't need the plus c part, right? Because I'm doing the definite integration here. So let me just continue with another color here. All right, this guy is equal to 2. So I have 2 times u to the 3/2. So now we can go ahead and find the value of the definite integral. So 2 times 4 plus t squared to the power of 3/2 from the lower limit 1 to the upper limit 4. Okay. If you plug in 4, 4 squared is 16. 16 plus 4 is 20. So 2 times 20 to the power of 3/2. I'm just keeping everything exact at this moment, not relying on to a calculator. Plugging in 1, 4 plus 1 squared is 5. So 2 times 5 to the power of 3/2. Okay. And now if you want to, you can go ahead and use your calculator to get an estimate. And you should be able to get 156.5 as the result of this integral. That is the arc length of x equals 6t squared and y equals 2t cubed from 1 to 4. And go ahead and, by the way, use your TI-84 to graph this curve. And I got right here. So it's a pretty long curve, in fact. As you see, like x's are ranging in between 0 and 100, and y's are ranging in between 0 and 120. No wonder the length of that. Think about this as a string clamped at somewhere here, okay? And this string has the length of 156.5 units, okay? All right, so this takes care of part A, and for part B, please move on to my next video and get ready for that one. All right, see you. Bye.